Hello, welcome back to tutorial series with PhysioDesigner. At the beginning of this tutorial, let's derive another formulation of Van der Pol equation than the one that we used in the previous tutorial. Do you remember that we could derive the Van der Pol equation by replacing a parameter k in the damping oscillation model by a nonlinear term of x, that is x squared minus 1. In the previous tutorial, we used two equations of the first derivatives of x and v for describing Van der Pol equation, but applying the same replacement of the parameter k to the single equation formula of the damping oscillation with the second derivatives, we can also have the Van der Pol equation, and adding a coefficient c to the equation to generalize it a little bit, we obtain the equation at the bottom of the slide. From this equation, we can derive a set of two first-order simultaneous differential equations. Firstly, let's introduce a new variable y, which is given by 1 over c dx dt plus x to the third power over 3 minus x. Once we solve this for dx dt, we can obtain one of two first-order differential equations. To obtain the other equation, we differentiate the equation of y by time. Then after some calculation, it provides that dy dt equals minus x over c. Finally, we obtained these two first-order simultaneous differential equations, which are the start point of this tutorial. Next, let's derive FitzHugh-Nagumo model. This is called FHN model. To derive FHN model, we have to add a parameter z to the equation of x, and add a linear term of y to the equation of y. FHN model is also known as Bonhoeffer or Van der Pol equation. This is a model of the membrane potential of neurons. For the first example, we will use the parameter value 0.7, 0.8, 3, and minus 2, for A, B, C and Z, respectively, and initial values for x and y are minus 2 and 3. Now let's create the model on PhysioDesigner. Because there are two dynamical variables in this model, let's create one module for each, so in total, the model is composed of two modules. At first we'll begin with a module for x. Click an icon in the toolbar to create a new module. Right-click on the module, and select Edit Physical Quantity. In the dialog, create the first physical quantity, which is a dynamical variable x. Select State for type, and set the name as x. Go to the Initial Value tab, and set the initial value as minus 2. Then move to Implementation tab to define the ordinary differential equation. Here in the text box at the bottom of the window, set the right-hand side of the equation, c times x minus POWX, 3, divided by 3, plus y plus z, and press Return key. Then you will see a dialog telling you that the equation includes physical quantities that you have not defined yet, and asking if you want to create them automatically now. Click Yes button. Those physical quantities are created automatically. Notice that they are going to be static parameter type of physical quantities by default. Now set the value for physical quantity c. This is an automatically created physical quantity, and just check that the type is static parameter type at the Basic Setting tab. Go to the Implementation tab to set the value. It is 3 here. Let's move on y. The dynamics of y will be implemented in another module, and here we just want to utilize the value by transferring it from the other module. So the type of the physical quantity should be variable parameter. We change it at the Basic Setting tab. Then go to the Implementation tab. The value comes to one of imports from the other module. So now the physical quantity must be assigned to an import. By this association between the physical quantity and an import, the value which arrives to the import is stored in this physical quantity. The combo box shows a list of imports. Now because there is no imports on this module, so it is empty, you can create a new import here. Give the name of the new imports in a text box, and click Add button. Then the newly created import is selected automatically in the combo box, and assigned to the physical quantity. That's all for y. At last, we go on Z. This will be a static parameter, so we don't need to change the type of the physical quantity. That is, no need to visit the basic setting tab this time. We change the implementation value to -2 at the implementation tab. Finally, we completed Module X. Click OK button to close the dialog. Next, we will create a Module Y. You can also create a new module from a context menu appearing by right mouse click. Set the name of the module in the dialog. Again, we will define several physical quantities in the Module Y. Right-click the module and select Edit Physical Quantity. At first we'll create a physical quantity Y, whose type is state, because this is a dynamical variable used in an ordinary differential equation, that is, it defines the state of the system. Its initial value is 3, and the right-hand side of the differential equation is -1/c times x minus a plus b times y. Then, again, it asks you if you want to create undefined physical quantities used in this definition. Click Yes button here. Move on to the physical quantity C. It is static parameter, so we again do not need to change its type, and set 3 at the implementation tab. Next is physical quantity X. Actually, this X is the same with the physical quantity X defined in the module X. We want to transfer the value from the module X to here. Hence here its type should be variable parameter type. We change the type at the basic setting tab, and at the implementation tab, we define an association between this physical quantity and an import. Because there is no import on this module, we need to create a new import. Put the name in the text box, and click Add button. The new import is now assigned to the physical quantity. Now we completed the module Y. Oops, we forgot to set the value of static parameters A and B, but don't worry, we can set the values of the static parameter type physical quantities easily without opening the dialog. Go to the physical quantity table at the bottom of the canvas. Double-click the cell in which the implementation of the physical quantity B is written. Then the cell becomes editable. Now set there, B equals 0.8. Similarly, for the physical quantity A, it should be A equals 0.7. Okay, next let's define the value transfer rules between the module X and Y. You remember that we need to transfer the value X from the module X to the module Y, and oppositely, the value Y from the module Y to the module X. Let's begin with defining the transfer of value X. From the gray triangle which appears when you put the mouse cursor on the module X, you can draw a line by drag and drop mouse operation to the import of the module Y. Now as you saw, an output was created on the module X, but it is red. Why? Because the newly created output is not assigned any physical quantity yet. It means the output does not know which value it should export. Right-click on the output and select Edit Port. In the dialog, you can edit the properties of ports. The list of the imports is shown in the upper part, and the list of the outputs in the lower part. You can change the port name by double-clicking the cell. Now just set X as the name. Then, this is more important, select a physical quantity to assign to this output, and click OK. Did you notice that the output became blue after assigning the physical quantity? Similarly, we need to define the transfer rule for the value Y. We can try the other way to create an output for Y. Open the physical quantity edit dialog. At Basic Setting tab of the physical quantity Y, look at the right side. There is a form to assign the physical quantity to an output. A list of outputs is shown in the white box if there are already some outputs. But now we don't have any outputs, so it is empty. We can create an output in this dialog. Put the name in the text box below, and click Add button. Then the new output is created. Selecting it in the list box defines the association between this physical quantity and the newly created output. After closing the dialog, you see, there is a new output, and it is already blue, because it has an association with a physical quantity already. Then click the output named Y, and drag and drop the mouse cursor to the import named X on the module X. Alright, Finally, we completed the model. Let's save the model into a file. Okay, now, let's check the dynamics of FHN model. Call Flint from the menu bar. Click Run button on Flint. This is a very simple model. The simulation finishes quickly. Go to the Detail and View. To draw a graph, move a name card X from the variable list box to the Y1 text box. There is a sharp raising following the quick drop. This corresponds to the discharge of the membrane potential of a neuron, which is referred to as a firing. To observe this dynamics on a phase plane, move X to abscissa, and move Y from the leftmost list box to the Y1 text box. The orbit started from the left upper position, went to right direction, and going to the left lower direction, and finally returned to the left upper position, and stops. The endpoint is a stable fixed point. So, all orbits started from anywhere on the phase space converge to this point. Considering the null lines of this system, you can understand the dynamics on the phase plane better. In the slide, the blue curve shows the X null line, and green line the Y null line. Notice that the stable fixed point is an intersection of two null lines. The stable fixed point is corresponding to the resting state of a neuron, and its X value to the resting membrane potential. Let's change the parameter value to see how it behaves under different condition. Go back to the main window of Flint, and go to Parameters tab. Double-click the expression cell of physical quantity Z, and change the value to -1. Click Run button to execute a new simulation. Then again go to Details and View, and drag and drop X to the Y1 box. This time, it periodically oscillates. Let's observe it on the phase plane. Move Y to the Y1, and move X to abscissa, and remove time. It shows a closed loop, which is a stable limit cycle. Geometrically, the change of the value of Z caused a position shift of the intersection of two null lines, that is the fixed point. We can understand this phenomenon as follows. The stable fixed point, which was stable before, lost its stability, and it became an unstable fixed point. At the same time, a stable limit cycle appeared, and the orbits twines around the limit cycle. This drastic qualitative change in the dynamics is called a bifurcation. Especially the bifurcation occurred here is a Hopf bifurcation. Then what happens if we use the value just in between -2 and -1 for Z? Let's check. This time, we will use -1.41314. We'll also change the initial values of X and Y. For X, it is -1, and for Y, it is 1.3. Okay, now run the simulation. X shows periodic oscillation. The waveform is slightly different from the one that we observed a while ago. On the phase plane, there is a stable limit cycle, but with again a little bit different shape. There is a small hump at upper left part. Next, we will change only the initial value of Y. This time, it is 1.8. Guess, what will the dynamics become like? X is still oscillatory, but the amplitude attenuates, and it will converge into a steady state. You can confirm this with longer simulation. This is interesting. All other parameters except the initial value of Y are the same with the previous simulation, but this time, the oscillation does not last stably. On the phase plane, it is rather clear that the cyclic orbit converges toward a fixed point. Superimposing these two orbits on the phase plane with null lines, the difference becomes clearer. In this situation, there are two stable states, one is a stable fixed point, and the other is a stable limit cycle. According to the initial point, the state falls either the stable fixed point, or the stable limit cycle. This kind of situation is called bistable. At last, let's investigate its bifurcation diagram. The abscissa of the diagram is the parameter Z, and the ordinate is value of X. In the middle of the dialog, there is a black curve, which corresponds to the fixed point. The center part of the curve is dashed, which is sandwiched by solid curves. The solid parts represent the stable fixed point, and dashed parts unstable. The endpoints of the dashed curve, that is the points at which the stability of the fixed point changes, are called the bifurcation points. From the bifurcation points, blue dashed curves come out to both up and down symmetrically. Two dashed curves grown from the left and right bifurcation points are linked by the blue solid curve. These blue dashed and solid curves correspond to the oscillation. Solid blue curves represent the stable oscillation, and dashed unstable. Actually, those lines represent the peak and negative peak of one cycle of the steady oscillation. When the value of Z is small, that is left side of the diagram, there is only one single solid black, meaning that there is a unique stable fixed point. And moving to a little bit larger Z, in the yellow shadowed region, there are black solid curve and blue solid curve, separated by the dashed blue curve. This is bistable region. If the initial point is inside of the unstable limit cycle, the state falls into the stable fixed point. But if the initial point is outside of the unstable limit cycle, it twines around the stable limit cycle. Moving further right side, that is larger Z, the fixed point becomes unstable, and there is only the stable limit cycle. Hence, all orbits starting from everywhere twine up to the stable limit cycle. More right side, again there is the bistable region. The fixed point is stabilized, but still there is the stable limit cycle as well. Then the stable and unstable limit cycle collide to each other and disappear. This is called double cycle bifurcation. Then the single stable fixed point remains in the system. By investigating a bifurcation diagram, we can better understand the system's dynamics. This tutorial finishes here. Thank you for listening. Goodbye till next time.